The change, I just can't read this problem. I think I'll just skip this problem, figure it out, because I just honestly can't even read what it's asking us to find. And it's already got the chart filled out, so this might not even be the best place to yeah, I'm going to skip that. I apologize, I can't read it. But here's an example that's just as lovely. Creating an ice chart. An ice chart stands for, what do we know in terms of initial, how much should things change by, and what do we have at equilibrium? Knowing it's the equilibrium that will be used, those concentrations that will be used to calculate Kc or Kp's if we're using pressure. So let's just take a peek at this example. Let the other one go. Find the value of Kc for the reaction. 2 methanes is in equilibrium with C2H2 and 3 H2s. All right. So note to self, Kc will be the concentration of C2H2 to the first power times the concentration of H2 cubed set over the concentration of methane, CH4, squared. And we calculate that with the equilibrium values, not the initials, not how much they change by, but the equilibrium concentration. So it's a Kc, so these will be molarity units, brackets. If we have this equation, we know how much we're starting with. So we start with all of the reactant, 0.115 molar units of our reactant methane. And we have no product. So you can, but in this example, we have 0 amount. We were able to detect the equilibrium concentration. So they're giving us as part of the problem, the equilibrium concentration of the acetylene, C2H2, was measured and found to be 0.035 molar. If we started with 0 and products get made, 0.035 molar was achieved at equilibrium. What we then know is that it changed by, again, notice it's positive because products get made, it changed by 0.035 molar units. This change column can now, with the help of stoichiometry, let us figure out the other change boxes as well to find equilibrium. Alrighty? So keep in mind what we know. We got to think about stoichiometry. The little ice chart I usually build like this. Initially, 0.115 and no products. The other piece of information they gave us, 0.035 molar units, was how much acetylene, C2H2, we had at equilibrium. So that's what we were given. I'm going to change color to say here's what we now know. That this was made 0.035 molar units. That's a positive value because products get made, reactants get used. How much of the reactant got used to create this much? Think about it as a stoichiometric ratio of want over given. Want over given. 1/2 of 0.115 was used during that reaction. Notice here, it's going down by the coefficient of a 2. And again, just peeking ahead. So, coefficient of a 2, and notice here, again, just kind of peeking ahead, that original amount of 0.035, that's how much was made here. So, put the coefficient and we get 0.035 of the original reactant was consumed. So the change would be twice of what was made here. Because of the coefficient 2. And it's negative because reactants get used. See the coefficient of 3? That's going to be placed here to keep in mind 3 times the amount of hydrogen would be formed based on its coefficient. So let's hit a little bit and see what we find. 2 times 0.035 gives us a change of 0.07. The original value, 0.115, minus how much was consumed, 0.07, gives us a net remainder of 0.45 molar at equilibrium. Here, 3 times 0.035 is 0.105. Added to the original amount of 0 gives us 0.105 molar units. We now have the numbers to plug in and solve for Kc. The equilibrium concentrations have been calculated from an ice chart. Initial change equilibrium ice chart. So concentration of our first product, 0.035, raised to the first power, its coefficient was a 1, times the concentration at equilibrium of hydrogen, 0.105, cubed, because its coefficient is a 3, over the equilibrium concentration of methane, CH4, raised to the second power, its coefficient is a 2. Products over reactants. With this ice chart, we were given initial amounts and one of the values and used stoichiometry to calculate the others. Let's hit this and get a common answer. 0.035 times 0.105 squared, cubed, backing up, divided by 0.045 squared. I get 0.02, again, no units. It's a number that's favoring the reactant side, 0.02. So here again is the process described word for word that we went through together. We used what was given to calculate equilibrium concentrations. The coefficients were distributed through this and out. Now what was nice with this problem is they gave us the concentration where the coefficient was a 1. So think of that as just distributing this coefficients through that value to achieve the 2 to 1 to 3, 2 to 1 to 3 stoichiometric